Morning, everybody. Morning. So, my name is Jason Ritchie. I'm the Chief Flight Instructor for Vincennes University. And some of you might know the Vincennes University Flight Program is actually located in Indianapolis now. We do the flight training out of the Eagle Creek Airport, which is over on the west side. And then all of our ground training and also our maintenance training is done at the International Airport at the Aviation Technology Center. We're actually the only school in the U.S. that has a fully functional 737 under roof that our maintenance students get a chance to work on. So if you're ever up in the Indianapolis area, make sure to come in and stop by and say hi to us. We'd be happy to show you around the facilities. So what I'm going to be speaking about this morning is the systems on the P47. So it's nothing too terribly in-depth, kind of a light overview. I'll take your questions as best as I can. I wouldn't consider myself an authority on the subject, but I'd like to think I've read enough that I'm fairly knowledgeable. So basically what we're going to cover is the power plant on the system. We'll touch a little bit on the if I can pronounce it properly, the turbo supercharger, propeller, fuel oil, and hydraulic systems that are on the aircraft. So first, this is where I talk about is the power plant that's on the airplane. The power plant on these is the R2800. The R2800 is a Pratt & Whitney engine. It is capable of producing 2,000 horsepower with the aid of the turbocharger that we'll talk about here in a little bit. It consists of a twin-row 18-cylinder engine. So actually a very, very large engine. It is supercharged with both gear and a turbine used on the engine itself to actually produce that 2,000 horsepower. As is with most engines back in that particular day, it is an air-cooled engine, so all open in the front, allowing air to pass over. And then we'll talk about some of the oil cooling that goes on the engine here a little bit later on. The system is an injection-type carburetor system. So it wasn't entirely fuel injected, but actually had an injection-type carburetor that it worked with. And then it also included a water injection system for what was called war emergency power, which is anybody in here familiar at all with war emergency power? So it was kind of an interesting concept. I got to read a little bit in it that for these engines they had a set operating parameter, but for emergency situations in wartime you were actually able to get an extra boost on the engine itself. Granted, it didn't last very long and it usually ended up tearing up the engine, but it was for emergency purposes if you actually needed it, kind of a suicide if you will. The system actually uses water and alcohol solution to prevent detonation. The process is started anytime that the throttle is moved within 1/8 of an inch of full forward. So in normal operations of the airplane, you want to be careful not to actually advance it all the way full to the stop, lest you'd actually get into this wartime emergency power setup that they have. This particular part will increase the power that the engine is capable of producing by about 15% of the maximum power. And like I said, you have to be careful with this. You'll only actually get about 15 minutes of operating time at this power setting before the engine isn't capable of taking anymore. So they always emphasized back then if you were going to use it, you used it only if you absolutely needed it. It was in emergency situations, usually if you were in a tight pinch in a combat situation, or if you had an emergency and needed an extra boost of power.
So what typically would happen if you did it for 15 minutes? Would it just lose power?
So
it
actually starts breaking down the engine, from what I understand. There was only enough of the water and alcohol solution in there to actually increase this power for about 15 minutes. Once the supply ran out and you'd actually run out of power at that point. Plus then the water and alcohol solution, as I learned from somebody a little bit earlier, actually was used to keep the temperature down on the cylinder walls. So you got that extra boost of power. The water and alcohol kept the temperature down. At that point, without that water and alcohol solution, you started running into detonation in the engine. Yes, sir?
Is there some kind of a stop or something on the throttle?
There's a safety wire.
Kept you from going
There was
over
a
that?
safety wire on that point that if you went up to and hit it, if you actually want to pass it, you would have to push through the safety wire to hit the full stop all the way up.
You're kind of excited in the battle.
No problem. Did
So,
you get there?
yeah, I was going to say, I'm assuming it was probably fairly durable wire because, like I said, you get a little excited. A little bit of safety wire isn't going to keep you from punching through that all the way. So, okay, the next thing we're going to talk about briefly is the turbo supercharger system that's on the airplane. With this particular system, max performance of the airplane is usually obtained between flight level 270 and flight level 300. Before I go any further on that, do I have any non-pilots in the room? Okay. If I get into aviation terms that you don't understand, stop and ask me, because some of this stuff is second language to me, but I can go through it and I'd be speaking Greek and you wouldn't quite get it. For when we talk about flight levels, it's anything above 18,000 feet. Us aviation folk like to think we're special, so we take normal words and convert them into something else. So anything above 18,000 feet, we drop a couple of the zeros and we put FL on the front of it. So flight level 270 is 27,000 feet, flight level 300 is 30,000 feet. But that's basically where you get your optimum power. The supercharger operation is actually a fairly simple operation, and it's in your textbooks. If any of you guys actually want to follow through on page 11, I'll actually just kind of read through the excerpt right from there. The supercharger operation is quite simple, and it's basically for any of you guys that have ever flown a turbocharged, supercharged airplane, or have worked on a car as a turbocharger, supercharger, it works almost the same way. Air compressed by an impeller that compresses the exhaust gas. That compressed gas is then pushed back up front into the engine that actually keeps the compression down, or increases the amount of compression. Basically, to give you a little bit of the physics of why you need a turbo or supercharger, as you go up in the atmosphere, the amount of oxygen you have up there stays the same, but the pressure actually decreases. As the pressure decreases, the engine has problems producing the same amount of power it does, just because there's a less dense amount of air. So what this system does, as does any turbocharger or supercharger system that you'd see on an airplane now and then the same up to this day, it recompresses that air to allow you to maintain the same power up there as you would down here. So basically the same function with oxygen systems or pressurization systems on an airplane. Like I said, the atmosphere is pretty much 17% oxygen from here almost to the edge of outer space. Just the issue is, as you go up higher, that the atmosphere is less compressed, so when you take a breath, you're not getting the same amount of oxygen as you are, which is either when you should get an airplane above about 12,000 feet, why you have to have a pressurization system or a supplemental oxygen system in order to keep breathing the same. So basically, this is an oxygen system just for the engine itself. So one other important note on there that I have to get to, otherwise this next slide's not going to make sense. The supercharged air is forced into the system via some intercoolers, and you can actually see, if I actually pulling this up, the intercooler is located right back around in there. Now the intercooler can actually be controlled inside the cabin itself. There is a shutter control located in the cockpit that the pilot can use to control this particular part of the system. Now there are three positions that you can see noted on here. There's a closed position, a neutral, and an open position. Normal operation of the aircraft, you'll want left in the open position except for cool weather. The reason for cold weather is the colder the air is, the more compressed it is. Basically, just like any time you heat up water on a stove, as you heat it up, air expands as it gets warmer. Same thing in an aircraft in the air. The colder it is, the more compressed the air is. The warmer it is, the less compressed it is. So as colder weather you get into, the less of a need there is for this to be open because the air is already somewhat compressed. This system must be in the neutral position if you're operating the aircraft above 350 miles an hour. That's basically just kind of for the standard systems. That way it can open and close as need be at that particular speed. The next thing that we're going to discuss on the aircraft itself is the actual throttle quadrant controls. Now there are about 4 different controls that you see on the aircraft, each of them, and this is actually in your textbooks, by the way, this particular graphic. These are probably your mixture control, which is actually what controls your fuel air and mixture going into the aircraft itself. The prop control, which I'll actually come to a little bit later on, which actually controls the governor on the propeller. This is your actual throttle quadrant itself, and then this is the boost control. And so 4 different levers, all of them having something to do with the engine. So now the turbo itself is pretty well controlled by this boost lever here, and these two can be linked together so that if you advance one, it'll automatically advance the other. So there is a disconnect, and there are certain situations where the disconnect must be enabled. One of them is obviously for starting. The other one is high altitude operations, because as you get up higher in the atmosphere, you're going to need to reconfigure the boost controller for the turbo more than you have the throttle, because at some point the throttle is going to be getting close to that full forward position, and then you're actually going to use the turbo to control the engine. Below 7,000 feet when operating the aircraft, these need to be unlinked. Now, the reason for that is usually at 7,000 feet is where they did most of the training maneuvers. With the training maneuvers, there wasn't any real need to actually use the boost, because most of that wasn't required until they actually got above 12,000 feet, and you get that loss of performance. So with the recommendation in the manual is anytime that you're operating, especially for training under 7,000 feet, the boost and the throttle need to remain unlinked. After you advance the throttle full forward, you'll use the turbo to maintain the manifold pressure. Getting off a little bit into the systems on how a constant speed propeller works. For most of you guys, if you've ever had a car that has an RPM gauge, you basically use the foot feed to control the RPM. Same thing pretty much in an airplane, unless you have a constant speed propeller in there. And then you get an extra gauge you have to mess with. One would be your RPMs, which in this particular case, and in this aircraft also, is basically controlling the propeller itself. Now the actual manifold pressure, which is what you basically use to set what power you want on the engine, would be controlled by the throttle. And so your prop lever is what controls your RPMs, and your throttle will control the manifold pressure. And so basically the way to think of it, if you wanted to convert it towards an automobile, was your throttle would basically control what would be your RPMs on that, except in an airplane you switch it around a little bit. That makes sense, or? Okay. All right, I didn't know they had a question about that.
Why?
He was visiting me earlier, so I'm glad to see you found another friend in my absence. Okay, so anyway, getting back to it, once the throttle gets to that full forward position, the boost is what you're going to use to maintain your manifold pressure. Okay, once you actually get to that point, very important that you always pull the supercharger handle back before the throttle. You do not ever want to get into a situation where you end up letting the throttle go behind the boost engine, because then you actually end up doing what we call an overboost on the engine, and that's how you end up cracking your cylinders or blowing a gasket or doing something else that's going to actually cause them to put another engine on the airplane. So very important in this particular aircraft that you make sure you know what throttle or what lever is supposed to be in front of the other one. So always make sure that boost handle basically would stay behind wherever your throttle is actually located on the aircraft. Okay, any questions over throttle quadrant and how actually to operate that?
Was there a pressure boost on the manifold? Would you have a relief valve?
On these, I'm not entirely certain whether they had, I believe, going through the picture, let me see if I can fast. These actually did have, that's going to take forever. I think these actually did have a wastegate on them. So yeah, actually they did. Now, depending on where that wastegate is set, and every manufacturer is a little bit different on how hard it would be or easy it would be to overboost the engine. I know, for example, on training aircraft, we have a system set up that it makes it almost impossible to overboost an engine. In fact, most manufacturers now on aircraft that are supercharged, or actually all are turbocharged now, the turbocharged will have what they call an automatic wastegate. That way, anytime if you accidentally overboost the engine, it'll blow throughout the wastegate. On earlier models, and especially back then, those wastegates had very specific settings that were put on them. So depending on exactly how excited you were getting when you were moving levers around is whether that wastegate would actually be able to keep up with what you're doing or whether you would end up overboosting the engine. So still, that's something still even today that we teach people that are working with turbocharged engines to be very careful about, as far as, you know, advancing throttles and then pulling them back, and then also the cool down times. So any other questions? Okay, so kind of also relating to the turbo itself, there is actually a gauge in the aircraft along with a light that displays where the turbo's at. The turbo itself is tack redlined at 18,250 RPMs. So the warning light that you see for the overspeed down there, this light is actually on as soon as the engine starts. There's a longer section in the manual that I'll let you read that talks a little bit about how and what the light should be doing as you're going through. But basically, the turbo is going to glow red until it's actually used. Now, once you're in the air going on, the recommended condition was you wanted to keep the light flickering on and off. You didn't want it completely off, and you didn't want it completely on either. But a steady flash between being off and on is actually the recommended setting. All right, and on the propellers on the aircraft has a 4-bladed Curtis Electric non-feathering propeller. For those of you guys that don't know the difference between a feathering and non-feathering propeller, a feathering propeller will actually, if something goes wrong with the engine and you need to shut it down, or something goes wrong with the engine and it decides of its own accord it's going to shut down, which is always more fun than when you actually do it on your own. With a feathering propeller, it will cause the blade to turn to a 90-degree angle. The reason for this being is it will have less drag as it's passing through the air. For example, everybody I'm sure as a kid, or even the current state as an older kid, if you stick your hand out the window when you're driving down the road, you can notice the actual change in resistance as you tilt your hand. Well, the resistance on that being called drag. If you have an engine, especially in an airplane that has more than one engine, if you have that engine that's not operating and creating drag, it's just creating more work for you as the pilot in order to maintain control of the aircraft. So what a lot of manufacturers did was they put this feather position on the propeller where you could bring it back. It would go into that 90-degree position and cause less drag on the aircraft, therefore making it more maneuverable. With these aircraft, partially, I imagine, since it was a single-engine airplane, and if you lose that engine, you're worried about more than just drag on the airframe. Don't have a fully feathered position. They are what they call a non-feathering aircraft. There are 2 controls that are available for controlling the propellers on the airplane itself. For those of you guys that are pilots, you'll find this. I found this rather fascinating. Because not only is there the actual throttle control on the quadrant that I showed you, but there's actually a selector toggle switch that is on these aircraft that's actually used to set the RPMs. Now,
so does that override the throttle, or why would you need the throttle?
The actual throttle setting is used basically for manual control. And pretty sure that I got it on here. If not, then when I pull the picture up, I'll explain a little bit more about it. But the actual prop lever itself on this, along with being able to manually control the governor, actually has a couple different settings on it. And one is whether it's in the automatic setting or in a neutral setting. So a lot of times if you were going to actually set it manually, instead of actually moving like in the traditional aircraft like we see today, where you'll actually move the prop lever back and forth to set the RPM on the engine, you're actually going to use the toggle switch to toggle it between a higher or lower RPM instead of actually moving the propeller, except for in a case where you have it set into the manual where that you'll actually use the throttle quadrant itself. Say if anybody has a little bit more knowledge on that, you're welcome to speak, because this is the first time I've ever seen a system like this, so I was kind of giddy reading through it. So this is the actual, and there is a graphic in your textbook about this. This is the actual prop control setup itself. So this is the actual prop lever with the increase and decrease, and then this is basically your 4-directional toggle switch on here. The up position would put it into the manual where it's set on an automatic setting. Pulling this toggle down will put it into the manual position, and then toggle left for a decrease in RPM and toggle right for an increase in RPM. There is also a circuit breaker that is associated with it, as with most systems in the airplane. You know, if there was some type of a problem with the system itself, the breaker will pop to let you know that there's a problem, and it also keep you from overloading the system. So I'm not going to touch too much on the emergency portions of it because we're going to have a presentation on that here later, but to just kind of give you an idea on some of it. Most of your prop problems on this, the Curtis Electric propellers are very inherently stable and non-complex, so usually you didn't see too many problems with the propeller system itself. Most of the problems that you got in the aircraft were actually caused by other systems on the airplane, chiefly the battery and the generator. For example, in the case if you actually get a weak battery, it'll cause the prop to hunt. And what we mean by hunt is you'll see a little bit of decrease in RPM and then an increase in RPM, decrease in RPM, increase in RPM, instead of it actually being steady. If in that particular situation comes up, you put the selector to manual and then use the toggle setting to actually set the RPM. With a generator failure, you're at this point pretty much running strictly on the battery. Provided the battery is fully charged at the time of generator failure, you're going to have about 1 hour of battery power at normal operation. Just with any particular emergency procedure where you have a loss of power in an aircraft, the first recommendation, which still very holds much true to this day, is you want to make sure to power off all non-essential electrical equipment, which in this case usually include the radios, where they'd recommend that the only time that you would need the radios is if you were actually coming back into the field to land to announce your position, or if it's a towered field to receive instructions from the tower at landing. Otherwise, the system needed to be off to try to conserve as much power as possible, because there are a few other systems we'll talk about that were dependent on the electric system. The recommendation on the prop, if you're actually close to the field, you leave it in the automatic position. If you are far away from the field, switch to manual and then control it with the actual prop lever or the toggle until you got closer to the field, and then put it back into the automatic position. Okay. Any questions over the propeller? Okay, the next system that we're going to discuss on the aircraft is the hydraulic system. And, the hydraulic system is pressurized by the engine-driven fuel pump, or engine-driven pump, getting into another system on top of that. The hydraulic system on this particular aircraft actuates the cow flaps, landing gear, and the wing flaps. Now the brakes on this aircraft are also hydraulic, but that is actually kept on a separate system, just in case for some reason if you have a failure on that engine-driven pump. That way, not only will you have the problem of the gear, the flaps, and the brakes, that system was actually kept separate, as it is still today on most aircraft, so that your brakes will actually be available. There is a hydraulic pressure gauge that is used to monitor the system. That particular gauge, which is shown there, normal operation on the system should be at about 1,000 psi. So that would be one of the things that in flight you would just want to casually check every now and then to make sure that the system was actually maintaining pressure. If not, then you might need to consider the fact of putting landing gear down, or actually getting the airplane into a different configuration for landing, depending on how quick you're losing hydraulic pressure. So, keeping on the systems that are attached to the hydraulic system, we'll talk about the landing gear. We have the actual picture of the landing gear shown on here. For this particular aircraft, the gear has 3 positions on it. There's an up position, a neutral position, and the down position, as shown on the actual diagram. So to move the lever on this, as you can see, there's actually a push button on the front. So you take the handle, push the button in, and then push down on the handle slightly in order to move it. Now, as with some modern aircraft, there is an additional safety system on here, because as you can imagine, especially on the ground, there's not too much of a problem with the gear being in the down position. It's accidentally getting it into the up position that you want to be careful of. So to raise the gear, there's a safety latch, which is, you can see right here, that not only would you have to push in this, you would also have to move that safety latch before you could actually bring the gear up. So a common rookie mistake, or if you get a little distracted and overexcited while you're messing with things, to actually be able to pull the gear up while you're on the ground. Okay, the flap lever, it's actually a pretty simple system with either a toggle for bringing flaps in the up position or in the down position. It is located immediately behind the gear control, so you actually have both of them right next to each other. The flaps, just like the gear, 3 positions on it: a neutral position, up position, and down position. Now, to prevent confusion between grabbing the gear and then grabbing the flaps, even though you know, there are different type handles and they actually have the push button in there, which is obviously part of the thing designed at night, so that way you're not fumbling between the controls. But they actually did set them 90 degrees apart from each other to avoid confusion. So that way you kind of had the muscle memory of, depending on where your hands were, as to which gear handle or which handle you'd be grabbing onto, so that way you didn't accidentally grab your gear handle and try to bring that up instead of thinking that you were bringing the flap handle up. Okay. Next system that we'll cover is the oil system on the aircraft. The oil system has a 28-gallon tank, normally a 19-gallon load, with a pendulum included in it for inverted flight. It is actually located in the upper part of the accessory section, which if you look down here is located right back around in this particular part of the engine itself. Also, for you guys that don't have an aviation, anytime we refer to the accessory part on the engine on the very back side of it is usually used to drive something else besides the propeller. We have some type of what we'll just call leach systems that they run off of the engine too, just like earlier I was referring to the engine-driven pump. So on the back of the engine, there are usually several different things that are attached to it that actually get its power from the engine. And so anytime that you ever hear somebody in aviation referring to an engine-driven pump or an engine-driven anything, it's attached to what is called the accessory case, which is located on the back of the engine. So like we said on this, for the oil system, it's located at the upper part of the accessory engine towards the back portion of the engine. The oil filler itself is located on the upper left portion of the fuselage, which the fuselage is the skin of the aircraft. So upper left portion in front of the cockpit. So when we're out actually walking around outside doing the pre-flight, we're on the left-hand side. If you look near the cockpit up front from that, that should be where the portion where you actually add oil to the aircraft will be. The oil coolers, which there's actually some air cooling that went on the oil. They're split doors that are located on the lower part of the engine compartment. So actually down towards the bottom where the air comes in is where the oil coolers are located. Now kind of referring back to the pendulum that we talked about this, the pendulum in there will allow the aircraft to fly inverted for about 7 seconds. So 7 seconds of inverted flight, it wasn't, it's designed as a fighter, not an aerobatic airplane, so it wasn't exactly designed to stay upside down for long periods of time. But in the need, obviously, for dogfighting and maneuvering, they build something in there so you can at least get 7 seconds of inverted flight in the aircraft before you start having some fuel and engine problems. So there is also an oil dilution switch that is located on the main panel. This, particularly if you have some type of problem where the oil is getting too thick, is used to thin out the oil with gasoline. Now, obviously, this isn't something that you want constantly running, so one of the things that the manual advises, and it also most likely be part of the checks, is you always want to make sure that that switch is set in the off position unless you're trying to dilute your oil.
What's going to be a need for diluting the oil?
That was something, and if anybody...
Yeah. Usually that's done when it's cold, it hasn't been started for a long time, it's for starting.
Yeah.
To lubricate it more easily, because it's really hard on the engine if you've got thick oil and it's cold and it's not getting throughout the whole engine.
And these engines use really, really thick oil. But nowadays, what we actually have is, there'll be an electric heater that has electric coils that'll wrap around the cylinders of the engine if you're using a piston aircraft. And there is an electric outlet. What we'll do is we'll just plug them in, almost like if you have a diesel truck, you have the heater on that. For piston airplanes, it works the same way, and it actually keeps the oil warm, so that way there's not a problem with it starting. Most of your aviation oil is such heavy viscosity that if you start it and run the engine, there really won't be that much lubrication for the first few seconds of actual aircraft operation, and then depending on how cold it is, maybe even up to a minute or two, which of course is very, very hard on the engine.
So does this dissipate then afterwards because of the heat? Is that what happens with the gas?
Yes, sure, yes, exactly. And you only put it on the switch for, usually it's a certain temperature of the oil, like that 20 degrees.
I'll be touching base on it a little bit during mine.
Good, thanks.
So we'll save that for a little later. Okay, this basically is your oil gauges that are located, and then the oil cooler on there. And then also, like I said, this is directly out of your manual. And it explains basically the function on the switch there. And this is actually to kind of help keep the oil cool. Obviously, either in the summer or if you're using high power operations, you're going to have almost the exact same or the exact opposite problem of what you're going to have with the cold oil, which is actually getting it too warm. So the oil cooler system on this can actually be varied depending on what your oil temperature is, so that you can regulate that. And then, like I said, except in cold weather, the cooler door should normally be left open. But if you're trying to trap engine heat, especially on the ground after a start, you keep those in the cold position until you got the oil warmed up. Okay, fuel system on the aircraft. There are 2 onboard tanks, and then there are also 2 wing drop tanks. And I believe, although I'm not entirely certain, on a later model of the aircraft, there's actually a belly tank that was also included. So you actually would end up with 3 external tanks on the aircraft. The main tank prior to the D25 model held 205 gallons, and the post D25 model held 270. As you remember from the earlier lecture, we were talking about that they wanted to have a 300 gallons total. As you can see, this number falls a little bit short. So the reason that you get that is you also have an auxiliary tank on board the aircraft that holds 100 gallons. So you either end up with about 305 or 370 gallons, just depending on which particular model of the aircraft you're flying is. Now, as we were talking about with the cutting board, that's the self-healing. Both your main and aux tanks on this aircraft have that self-healing type of material on it, so that if you are get a puncture from a bullet or something, it should seal itself back up so it actually isn't leaking fuel. The filler neck for the main tank is located on the right side of the fuselage, so the right side of the aircraft, up in front of the cockpit. The filler neck for the aux tank is in the right wing root, which what I mean by wing root is the part of the wing that's closest to the fuselage below the cockpit. So those you'll actually be able to see outside on the airplane when we walk around it here a little bit later. Fuel gauges on the aircraft are electric, and they are accurate in level flight only. So, which obviously most of your gauges back in that particular time were float gauges, much like what you see on your lawnmower nowadays. So it's just a simple float type operation. So obviously, with this being a tail wheel aircraft, once the tanks are tilted, you're going to get kind of an imbalance of where the fuel's actually shown. So the only time that it'll be accurate is when you actually have the tail up and the airplane's level. Now, they do consider the gauges to be unreliable anytime that you have under 20 gallons of fuel on board. You'll also get a fuel warning light anytime that the mains have less than 40 gallons. Just kind of letting you know that you're getting into the danger area. Your fuel pressure gauge on the aircraft, located on the instrument panel. Normal operation for the aircraft is between 16 and 17 psi. You should see right around 7 psi at idle operations right after starting. So these are the fuel selectors on the aircraft. You actually have 2 of them. And I'll go through and kind of explain how those are actually set here. Fuel is drawn from a tank by a variable speed boost pump and then forced into the carburetor by an engine-driven pump. The fuel selector, depending on what you have it set on, will turn on the pumps automatically. So 2 different selectors. You have your selector, and this is basically where the hole is, that's your toggle. So whatever you have that set to is which tank you're going to draw off of. So as shown in the picture here, this would be with the fuel system set to off. If you flip it 180 degrees around to the front part here, this is feeding off your main tank. If you flip it to the right, you're feeding off your auxiliary tank. Now the left will feed off the external tanks. Once set on the left, you then come to your second fuel selector and then figure out which one of those tanks you'd be feeding off of, either left external tank or right external tank. So main aux, like I said, are a single selection, and then the wing tanks are selected through the external setting on that itself. Okay, so caution on fuel management in the aircraft. They actually had a really good picture I stole out of the book on there. So there are no gauges on the wing tanks. So once set on the wing tanks, you have to know exactly how much fuel you're burning an hour, and then you have to pay attention to your watch. As anybody that's went through flight school has told you, this is an essential piece of equipment that you have to carry with you at all times. So once you know what your fuel burn rate is and how much fuel you have on board, do your calculations, and you have to make sure that you are staying on target with whatever your fuel consumption is. Another thing that you would have to be aware of that would actually affect the handling of the aircraft is making sure that you're alternating between the two tanks to make sure that you have a balanced fuel load. As obviously, if you draw one aux wing tank completely dry and the other one's full, it's probably going to land a little funny. Not to mention fly a little bit funny. You're going to wonder why you have to stick one way or the other constantly while you're in flight. Same very much applies today for some of the training aircraft that we use. Although, well, of course, same thing with today. If you end up running a tank dry, you usually only do it once as a student, and then it's very well burned in your memory to go back and forth and make sure that you're properly switching back and forth between your other tanks. Obviously, if you're starting to see a fluctuation in your fuel gauge, that's an indication that you might need to change tanks. It's recommended in the manual that if you see a fluctuation, regardless of whether you think your timing calculations are correct or not, to go ahead and switch tanks just in case there might be fuel impurity or something that could actually start the engine of fuel. The other recommendation, take off on your main tank, and then once you're actually in flight, switch to the aux, and then fly on that 10 minutes before switching tanks. The other recommendation, if you're not using external tanks, use the aux fuel first, and then go back to your main tanks. So, and that concludes systems on the aircraft. Any questions?
During war, you talked about hydraulics and also the oil. The flak that was thrown up during war, and also bullets. We had the repairing of the gas tank, but did they have a lot of problems with the hydraulics, gas, or the oil and the hydraulic system during war?
Usually, those two systems are buried in close enough to the engine that if you were going to take a lot of bullet shots to that particular region of the aircraft, odds are you were going to have a lot of engine problems just as much as you were hydraulic or oil problems. However, if you were to take a hit to the hydraulic system or the oil system, since neither of those are considered explosive, granted the oil is somewhat flammable, that was the main concern for having the self-healing fuel tanks, because even if you didn't explode when a bullet punctured through and ignited the fuel, with a leak, you only had a certain limited amount of time to be in the air. Granted, the same thing would be pretty true with the oil system, but the hydraulic system, if you end up taking a bullet, break off from the combat situation, you would basically need just enough hydraulic fuel or hydraulic fluid in the airplane to get the gear down. Are you going to cover the gear emergencies? Okay. There's also, like I said, I'm not going to steal any of his thunder. There's also a manual way to get the gear down, but it provides that you still have some hydraulic fluid left in the system. But it's not exactly considered an essential component for combat. So if need be, you can still fight in the mission. Once you're out of hydraulic fluid, you can always go back to the airport and then do what us pilots like to affectionately refer to as a belly slide, and then bring it in on its belly. Obviously, if you're going to do that, you should probably ditch the fuel tanks if you have them on the outside. Otherwise, you have a slightly bigger problem. But that, for that particular reason, is why those weren't considered as essential as what your fuel system would be. Any other questions? Yes, sir.
Do you have any excess of parts for those things, like carburetors? things of that kind of thing that are not usable, but still look like the object?
So, now these actually did have carburetors on them. But you know, what was the
Well, we've got a P47 engine we're trying to restore for the museum, but it's got a lot of those kind of parts missing.
okay.
He's looking for a carburetor part.
Well, if I happen to come across one, I'll let you know.
All right.
There you go.
So,
Just
any other
to,
questions?
just to address that question about the oil, that, as I mentioned, I run an oral history program, and I've interviewed at least 3 dozen P47 vets, and there are stories that they tell of complete cylinder heads being knocked off the engine. So you got oil just gushing out of a missing cylinder head, and they've still flown 2-3 hours with the missing cylinder. So, I mean, from somewhere over Europe all the way back across the channel, pumping oil out of a missing cylinder head. So, I mean, was it essential? Yes, but the P47 could handle it.
It's just about like, you know, if any of you guys have had younger kids, you know, with their first car, a lot of times they'll discover that, you know, the car will run without oil. It just may not run for very long. So, same thing pretty much applies with an aircraft.